Hey there guys, so here I'm trying something a little bit different for my channel. We're going to go through a physics paper. Now if you'd like to see more science content on the channel, be sure to give this a thumbs up and let me know down in the comments. So this particular paper is AQA's Specimen 2018 Higher Physics Paper 2, which is the one I get the most requests for. So I got no idea how long this is going to take. Hopefully we're going to have fun. Let's get cracking. Okay, something I didn't say was that I will link the paper down below in the description so you can play along. So, for question 1, a student suspended a spring from a laboratory stand and then hung a weight on the spring. Figure 1 shows the spring before and after the weight was added. 1.1 wants us to measure the extension of the spring when the weight is added. So, if we drew a line across from the bottom of the spring before the weight was added, we are at 10 centimeters, and then do the same for when the spring was added, and we're now at about 11.3 centimeters. So we've extended from 10 centimeters to 11.3, and that is 13 millimeters. Then we're told the student used a spring, a set of weights and a ruler to investigate how the extension of the spring depended on the weight hanging from the spring. Before starting the investigation, the student made the prediction that the extension of the spring will be directly proportional to the weight hanging from the spring. Seems logical. So, figure 2 shows how the student arranged the apparatus. So, hopefully there's a really obvious problem here. The ruler is wonky. So, it's not a very good setup. 1.2 tells us before starting the investigation, the student rearranged the ruler so that it was vertical. We want to explain why this is important. So when we come to the writing questions, I'm just going to talk through them, not do the writing, because my writing is terrible. So if the ruler wasn't vertical, then it's not aligned to the extension of the spring. So the readings that we would get from the ruler would be inaccurate. So we need the ruler to be vertical, so it's parallel to the extension of the spring, and then we can read accurately the extension of the spring. The student measured the extension of the spring using a range of weights. The data, the student's data is shown plotted in figure 3. So we got our weights going along the bottom and the extension of the spring going up the side. 1.3 asks us what the range of weights were that the student used. So the smallest weight we used was this guy, which was 1 Newton, and then the biggest was this guy, which was 6 newtons. So the range of weights was 1 Newton to 6 newtons. 1.4. Why does the data plotted in figure 3 support the student's prediction? So remember, their prediction was that the extension will be directly proportional to the weight. Direct proportion has to be a straight line and it has to go through the origin. So that's how the graph supports the prediction. We've got a straight line that passes through 0, 0. Okay, then 1.5 one says to describe one technique we could have used to improve the accuracy of the data the student collected. So for this, we could talk about the placement of the ruler, put the ruler directly behind the spring. We could talk about how we could line up the bottom of the spring nicely with a point on the ruler so it's easier to read the measurement. We could put a horizontal pointer on the bottom of the spring that goes across to the ruler and points exactly at the measurement we want. Anything like that, and we are golden. The student continued the investigation by increasing the range of weights added to the spring. All the data is plotted as a graph in figure 4. So what we can see from this is the data stops living in a straight line after about 7 newtons. It's then become a curve. So that means that the extension and the weights are no longer in direct proportion. As the weights increase after about 7 newtons, the extension speeds up. So we're no longer talking direct proportion. So at the end of the investigation, all of the weights were removed from the spring. What can we conclude from figure 4 about the deformation of the spring? So we know in real life we can pull a spring and it will bounce back to exactly how it was unless we pull it too far. At that point we have inelastically deformed the spring because it won't bounce back to its original state. It will stay stretched. So we can say the spring has been inelastically deformed, and we're asked to give a reason for our conclusion, and the reason would be that it's the weight and the extension are no longer in proportion. So we could say it has exceeded its elastic proportionality. Okay, question 2 is about space. So space is cool. In 1929, Edwin Hubble observed the light from galaxies that are moving away from the Earth at longer wavelengths than expected. We are asked what name is given to this effect. So it's the redshift effect. So things moving away from us appear red, things moving towards us appear blue. Red has a longer wavelength than blue, that's the reason why. Okay, then 2.2. From his observations, Hubble was able to calculate the distance and speed of a galaxy away from Earth. So we've got his results down here in this graph. So we have distance going along the bottom and speed away from Earth going upside. We are asked what relationship between the speed and distance of a galaxy is suggested by these results. So we can see there is a general trend that as the distance along the bottom increases, so too does the speed of the galaxy. So we could say the further a galaxy is from Earth, the faster it is moving away from us. The observations made by Hubble support the idea that the universe is expanding. This means that galaxies are continually moving away from each other and from the Earth. Figure 6 shows a student using a balloon to model the idea of an expanding universe. Shows some dots which represent galaxies were marked on the balloon, and then the balloon was inflated. We are asked to give one strength and one weakness of using this model to represent an expanding universe. So the strength, think about what happens as you inflate a balloon. The outside of it becomes bigger and bigger. So it's stretching. So the strength I would go for here is it does give a good representation of the galaxies moving away from each other, because the dots will move away from each other. On the flip side though, there are two things I can think of with the balloon. First of all, you can't keep on inflating a balloon. It will pop. The universe supposedly can continually expand without ever popping or imploding. So that would be one weakness. We cannot keep blowing up the balloon forever, and also the dots are only drawn on the surface of the balloon. In reality, the universe is packed full of galaxies. They are not just around the surface of the universe, if you like. They are completely throughout the universe. So for this model to be even better, we would somehow want dots on the inside of the balloon as well. But obviously, we can't really do that. In the 1950s, there were two main theories to explain how the universe began. Theory 1 was that the universe has always existed, it continually expands, and new galaxies are formed when older galaxies die out. Theory 2 is that the universe began from a very small region that was extremely hot and dense. The universe has been expanding ever since. So we are asked, in what way do the observations made by Hubble support Theory 1 and Theory 2? So his observations suggest that the universe is expanding. Both theories suggest that the universe is expanding, so that is how Hubble's observations support both theories, that the universe is expanding. Most scientists believe Theory 2 is correct. So just what is likely to have caused scientists to start thinking Theory 1 is wrong. So these two theories were around in the 1950s. Think about the technological advances that have happened since the 1950s. More and more, we are finding more evidence that supports Theory 2. So that supports like the Big Bang Theory, its computer simulations and stuff, get better and better. We find more evidence that cannot be explained by Theory 1. So more and more, we are in support of Theory 2. Okay, question 3. So a student investigated how the magnification produced by a convex lens varies with the distance d between the object and the lens. So the student used the apparatus shown in figure 7. So we got our ray box. Very importantly for this question, the object slit is 1 centimetre. So then we got the distance d between the object and the lens, and then we got the screen on the right with the shape image. So 3.1 says the student measured the magnification produced by the lens by measuring the image height in centimetres. Explain why the image height in centimetres is the same as the magnification. So remember, magnification is the image size divided by the object size. Here, the object is 1 centimetre tall. So, here the object is 1 centimetre. So, when we've divided the image height by 1 centimetre, anything divided by 1 is that thing itself. So here, because the object is 1 centimetre, the magnification is exactly the same as the image. Data collected by the student is in table 1. So we got distance between the object and the lens in centimetres on the left and the magnification on the right. So we can see as the distance increases, the magnification decreases. Now we are told it would be difficult to obtain accurate magnifications for distances greater than 60 centimetres. So the reason for that is we can see on the right the magnification is getting incredibly small. So we're at 0.5. So we want to suggest one thing that we could do to obtain accurate readings for magnification with distances greater than 60 centimetres. So the one that strikes me first of all would be to use a bigger object. If we had a bigger object, that's going to make the image bigger and easier to measure. So that would be the main one I would go for. We could maybe put a scale on the screen, and then that's going to start getting ridiculously small. So we'd have to probably then read that with a magnifying glass. The one that I would go for is use a bigger object. That is going to be the easiest fix. The graph in figure 8 is incomplete, so we need to fill it in. So we need to complete the graph by plotting the missing data points and then draw a line of best fit. So, the first data point that's missing is the one for 25 centimetres. So we find 25 along the bottom, and then 4 on the side. So 25, 4 is this point here. Then we got 30, 40. The next one that's missing is 50, which has a magnification of 0.7. So 50, 0.7 is this point here. So what we now want to do with those points is join them up using a curve. So we should get something that looks like this. Okay, so an artist I am not, but we should get something that looks like that. Okay, then the next question asks, how many times bigger is the image when the object is 35 centimeters from the lens compared with 55 centimeters? So, we need to find estimates. They are only estimates because this curve is crap, of the size at 35 centimeters. So we're going to go up from 35 until we hit the graph. So I'm going to say that's here. Now that will go across to 1.4. So we got 1.4, and then we do the same at 55, go up until we hit the curve. So let's say it's about there. So that's going to be about 0.6. So to work out how many times bigger 1.4 is than 0.6, we do 1.4 divided by 0.6, which is about 2.3 times bigger. Okay, next we are told in the investigation the student also measured the distance between the lens and the image. Table 2 gives us both the distances of the object to the lens and the lens to the image. So we've also got our magnification in there. We are told to consider the data in table 2. So let's consider it. There we go, we've considered it. We want to give a second way that the student could have calculated the magnification of the object. So, can we see any link between these numbers? So let's look at the top. We've got 100, 25 and 4. Are those numbers linked? Well, yes. 100 divided by 25 is equal to 4. So that works. Let's see if it works for another one. Let's go 60 divided by 30. Oh good. That's also equal to 2. So what we could have done is distance between the lens and the image divided by the distance between the lens and the object, and that would give us the same numbers for the magnification. 3.6 wants us to complete the ray diagram to show how a convex lens produces the image of a close object. So, here is our ray diagram as it starts. Our object is between the focal point and the lens. So our image is going to end up to the left of the left-hand focal point. So the first thing we want to do is draw a straight line from the top of the object through the centre of the lens. So that will look like that. The next thing we need to do is draw a line from the top of the object that is parallel to the x-axis, if you like. So that's going to hit our lens like that. Then we draw a line that goes from that point through the right hand focal point. So that's going to look like that. So we can see like this, these two lines on the right are not going to meet on the right of the lens. So what we're going to do then is carry on each line up and to the left, like this. So this point up here, where they meet, is going to be the top of the projected image. So our image looks like that. Cool. Okay, question 4. Figure 10 shows a straight piece of wire passing through a piece of card. A current I is passing down through the wire. We are asked to describe how we could show that a magnetic field has been produced around the wire. So given that the wire is passing through a piece of card, the first way that I thought of was to put iron filings on the card, move the card around a bit, and the iron filings will arrange themselves in a pattern of the magnetic field. The other way that the mark scheme suggests is to move a compass around the wire, and what will happen is, because compasses work because of magnetism, if there is a magnetic field, and then the needle will change direction as we move it around the wire. 4.2. Figure 11 shows the ignition circuit used to switch on the starter motor in a car. The circuit involves an electromagnetic switch. So here's our complete circuit. We want to explain for 4 marks how the ignition circuit works. So for 4 marks we need to be pretty thorough. Okay, so starting down here in the bottom right, we've got our 12 volt battery. Now if we go up to the top, this really is where our story starts, with the ignition switch. So when we turn the key in the car, we are closing the ignition switch. That then allows a current to flow to the electromagnetic switch. Now when the electromagnetic switch has a current flowing through it, the iron core will become magnetized. Now when the iron core is magnetized, the iron arm, which is on a pivot, or even the short part of the iron arm, is going to be attracted to the iron core. So this arm is going to hit the magnet. This arm is going to hit the magnet. Now, in this arm is going to push the starter motor contacts together. So then, when the starter motor contacts make contact, the starter motor circuit is complete. So a current is then flowing through the starter motor. So the starter motor will start. Cool. Question 5. The data in table 3 was obtained from an investigation into the refraction of light at an air to glass boundary. So we got our angles of incidence and our angles of refraction. We want to describe an investigation that a student could carry out to obtain similar values. Our answer should contain any cause of inaccuracy, and we may use a labelled diagram in our answer. So, angle of incidence is the angle at which a light beam hits the normal to a surface. Now, a normal is a straight line at 90 degrees to a surface, so it's perpendicular. An angle of refraction is then the angle between the normal and the refracted ray once it's passed through the surface. So we want to think about an investigation then where we could investigate this. So we are going to need a glass box or a glass block. First of all, what we're going to do, we're going to put that glass block on a sheet of paper and we're going to draw around it. Once we've drawn around it, we're going to take the glass block off, and then on one of the sides of this rectangle, we're going to want to draw a normal. So a line at 90 degrees to the block. Now, I've drawn a little diagram down here. So here, the blue rectangle is the outline of our block. The red line is the normal, which I would draw through the outline of the glass block too, so then we can measure our angle of refraction. So, once we've got the outline of our block, and we've got our normal drawn in, let's say we wanted to investigate the first value, where we have an angle of incidence of 20 degrees. So using our protractor, we would want to measure in this angle of 20 degrees between the normal and what is going to be our light ray. So measure off 20 degrees, put a mark, draw a line then on the sheet of paper. At that point, we now have the line that we want to shine our ray of light along. Okay, so once we have that line drawn, we can put our block of glass back on the piece of paper, and then using a ray box or a laser, something like that, shine a beam of light along this line so that it hits the glass at the point that the normal is drawn, and then we will see where on the other side, so down here, we will see where the beam of light comes out of the block. So if we mark that point on, we can then take the ray box away, take the block of glass off, and that is then going to allow us to draw the refracted beam of light inside the glass by joining up the point at the normal and the point that we just marked on the bottom. From that, we can then measure our angle of refraction between the normal and the refracted beam. So, to obtain the data in the table, we could repeat that process with different angles of incidence. So as far as the investigation goes, we would want to write down pretty much all of what I just said. It is 6 marks. It also said to include any causes of inaccuracy. So this could come down to misreading the protractor. More importantly though, the thickness of the light beam might make the angle hard to read. Oh, that was a fun one. And then 5.2 says to state the reason that light is refracted as it crosses from air to glass. Light moves slower through solid objects than it does through air. So because it slows down, it is refracted. Question 6, so figure 12, shows the construction of a simple transformer. So we have an AC input which goes to the primary coil. We've then got an iron core, and then our secondary coil, and then our output. 6.1 asks, why is iron a suitable material for the core of a transformer? So transformers work because of electromagnetism. The reason we use iron is because it's easily magnetized. Okay, a student makes 3 simple transformers, J, K and L. Figure 13 shows how the potential difference across the secondary coil varies as the potential difference across the primary coil is changed. So here's our graph. So we got potential difference across primary coil along the bottom, potential difference across the secondary coil going up the side. So first of all, we are asked, how can you tell that transformer J is a step down transformer? So in a step down transformer, the potential difference in the secondary coil is less than the potential difference across the primary coil. So if we look at J, the primary potential difference is 6 volts. The secondary potential difference is 4 volts. So we can tell this because the potential difference across the secondary coil is less than the primary coil. Okay, then for 6.3 we are told each of the transformers has 50 turns on the primary coil. We want to calculate the number of turns on the secondary coil of transformer L using the correct equation from the physics formula sheet, which by the way is linked down below. So the formula that we want is potential difference of the primary divided by potential difference of the secondary is equal to the number of coils on the primary divided by the number of coils on the secondary. So for transformer L, potential difference on the primary is 6, potential difference on the secondary is 12. So we know 6 over 12 is equal to, well, there's 50 coils on the primary, so 50 over the number of coils on the secondary. Okay, 6 over 12 is 0.5, so 0.5 is equal to 50 divided by the number on the secondary. So we can multiply by the number on the secondary. So number on the secondary times 0.5 is 50. So if we then divide by 0.5, we get the number on the secondary is 100. So there are 100 coils. Okay guys, I'm going to call that a day for part 1. This is, after all, just an experimental video. If you found this useful, let me know down below. Give us a thumbs up. I'll do the rest of the paper, and I'll try and do some more science stuff for you. Let me know what you want.